So as we've been going along and studying rotational motion, you might have noticed that we seem to be defining terms that are really equivalent to some linear term that we've learned before. For instance, we learned that angular velocity, which is omega, really is the rotational equivalent to regular velocity. Angular acceleration, which is alpha, is the equivalent to linear acceleration, which is a. And in fact, we found that in situations where the angular acceleration was constant, that we came up with kinematic equations that were exactly in the same format that our linear kinematic equations were for constant acceleration. Shouldn't have been a big surprise though, because those terms are very closely related, angular and linear. So we get to the point where we've defined a lot of rotational terms that seem to have some relationship to linear terms. So we get to the point where we might ask the question, is there a rotational equivalent to Newton's second law? That is there a rotational equivalent to F equals ma? And to be honest, at this point, because we've really been introduced to basically all the rotational equivalents to these terms right here, we might hazard a guess and say that it's going to be equal to torque is equal to I times alpha. Why? Torque is basically what we get when we apply a force in such a way that it causes a rotation. So torque is really the rotational analog to force. We just learned about moment of inertia, which is the rotational inertia of an object. And in linear terms, we defined inertia by the mass. So we replaced the mass by I. And then finally, we have the angular acceleration because that is the angular equivalent to acceleration. So that's our hypothesis, but we can't just assume that we're right because we all know what happens if we assume. So let's look at a scenario where we can show that we can come up with this expression. So in this picture right here, we have a mass on a frictionless table, and the mass is attached to a string so that it can travel on a circular path. Now, in order to make that mass move and to accelerate it, we're going to apply a force that is tangential to the path, and that's what that force is right there. Notice it says here that the force is perpendicular to the radius, so that force is tangential. So let's just write that down. So if we think about it, that tangential force would be applied to that mass and would cause a tangential acceleration. But of course, because it's going in a circle, we also could write that tangential acceleration in terms of its angular acceleration, because that mass will also have a rotational acceleration. So we could write this as m alpha times r, because alpha times r is just equal to the tangential acceleration. Now when we think about it, that force, because it's perpendicular to the radius, it actually is going to cause a torque on the mass, because it's a force that's applied so that it's going to cause a rotation. So if I multiply this entire term by the radius, because of the fact that in order to calculate the torque caused by this force, because it is perpendicular, we would just have to multiply it by the radius, and that would give us the magnitude of the torque, the radius times that tangential force. And so we'd have r times F tangential is equal to m alpha r squared. That's what we're left with right here. Now, I'm going to sort of group things differently. I'm going to write mr squared times alpha, just to make it a little more obvious. Now the left-hand side, which is the radius times the force, that tangential force, that's just the torque. And mr squared, for this particular scenario, is really just the moment of inertia of that particular mass as it rotates about the axis that is going down through the center of the table. So that's equal to I, and then we're left with alpha. So we did find that this torque equals I times alpha can be used to describe this particular motion. And while we did use something very specific, it does turn out that in general, this relationship is true. So it is true that the rotational equivalent to F equals ma is torque equals I times alpha. So if we have an object that is rotating and experiencing an angular acceleration, it'll be caused by some sort of torque acting on the object. And it'll also be influenced by the moment of inertia of that object. And we'll take some time in class to look at some examples. All right, see you soon.